Hello fellow problem solvers, so today we're going to be doing a problem from the Asian Pacific Math Olympiad 2021, problem number 1. I suggest you try this problem out for a minimum of 20 minutes, ideally 45 to an hour, but not more than 2 hours. If on the other hand you'd like to go along with us, I suggest you give it a go for the next 20 minutes. So now, let's begin. So this is the problem. We have r is a real number greater than 2. And we must show that this equation right here has two or three solutions for every single r. So now let's think about this. So like first and foremost, this is positive, so x needs to be positive. But what does this sort of look like? Let's maybe take r is equal to 3. Like why does it have to have two solutions? Like I can see 1, x is equal to 3. That gives you a solution. 9 squared is, what is this going to be? 3 times 3. Now, what other solutions are there? And okay, what if we have the floor of x is 2, then we have 2 times 3, we need to make this equal to, okay, square root of 6, we just need the square root of 6 to be greater than 2 and less than 3, so this is true, so the square root of 6 is another solution. Is there a solution of 1? We would have 1 times r is 3, would need to be equal to x squared, and x would be equal to the square root of 3, needs to be less than 2, greater than 1. It is. Okay, so this is how we can get more than one solution. Like this is an integer, a positive integer, and then that sort of bounds what x squared can be. Now, if you didn't have this sort of insight before, I invite you to pause for another 5-10 minutes and try to push the problem further. And also here with 4, why do we have an issue? If it's 4, we need 4 times 3 is equal to x squared, which means x is the square root of 12. But this is less than 4, so like there's some sort of bounding that's happening here, and we need to figure out what that bounding thing is. Now, how do we proceed here? Well, a way to quickly formalize this is to say, like, let the floor of x be equal to n, and we need that x is equal to n plus some epsilon, where epsilon is greater than or equal to 0, less than 1, and we have n plus epsilon squared is equal to what? N times r. Now for us, we don't really need to find epsilon here. We just need to show that there exists an epsilon here. So the only thing we really need is for that epsilon exists. So what's enough is to have n times r be greater than or equal to n squared, the smallest epsilon can be, and less than n plus 1 squared. If this is satisfied, we can find an epsilon. And this is a big shift here in this problem, because you're no longer looking for a specific epsilon, but you're saying, if this bound is satisfied, I will find my epsilon. And it is with this idea that I invite you to pause for another 5-10 minutes and push the problem further. So now there are really two things to do. One is to show there exists at least 2 such that this is satisfied, and the other one is to say there don't exist 4 n for which this is satisfied, for natural numbers n. And now what is one that will quickly satisfy this? Well, it's the floor of r, because what do you have? The floor of r times r is greater than or equal to the floor of r squared, just due to the fact that r is greater than or equal to the floor of r squared. And this side is also satisfied, the floor of r plus 1 squared, because this thing right here is greater than r. And this is also greater than this thing. So we have one solution. And if you look back to our 3, we had the floor of 3, which was 3, and we had 2 and 4. So maybe there's something about plus and minus. Actually, no, we had not 2 and 4. We didn't have 4. We had 2 and we had 1. So maybe the floor of r plus 1 doesn't work. Actually, does it work? I don't know. Now it's time to figure that out. So for the floor of r, actually, we can simplify this. This means that r needs to be less than n plus 1 squared over n and greater than or equal to n. And now we know that the floor of r plus 1 doesn't work. So this means that the floor of r is a solution, and you would expect that the other solutions, and the floor of r plus 1 is not a solution, so you'd expect that the other two, that this floor of r minus 1 should somehow be a solution. Maybe, is it? Well, let's push it and see what happens. So what we need this to be satisfied. Now what happens with the floor of r minus 1? Well, this thing right here becomes the floor of r squared over the floor of r minus 1 needs to be less than r, greater than or equal to the floor of r minus 1. Okay, so this is already satisfied. We don't have a problem with this. Now let the floor of r be equal to t, and r is t plus some epsilon. We know t is greater than or equal to 2 because of the problem statement, and epsilon is between 0 and less than 1. So now what does this give us? It gives us that t squared is greater than r times, so r is t plus epsilon, times the floor of r minus 1. What is that? Well, that is t minus 1. So what does this give us? Well, it gives us that this is t squared less than t squared minus t plus epsilon t, and we have minus epsilon. So now this gives us t squared goes away. We have t plus epsilon needs to be greater than epsilon times t. Interesting. Now, is this true? We should be able to factor this. This is t, I believe this is t minus 1. Epsilon minus 1 is less than 1. If I'm not mistaken, that's the factoring. Like if I take these on the other side, I add 1s, yes. And this is the factoring. And we know this is, wait, this is definitely true because epsilon is, this is negative, and then this is positive, so this is definitely less than 1. So this is definitely true. Oh, I didn't get that. So it seems like the floor of r minus 1 is also gives us a solution here. And now with these insights, I invite you to push the problem further a bit for the next 10 to 20 minutes. Here's the next step. So this is what we have. We have this sort of relationship right here, and we know these things to be true. We know that the floor of r and the floor of r minus 1 satisfy these relationships. So now what we need to prove is that the floor of r minus 2 and something even less than that doesn't satisfy, and then we'll be done. So now let's set n to be equal to this, and let's actually set the floor of r to be equal to t. R is equal to t plus epsilon. And now what does this give us? Well, this is satisfied, but we have n plus 1 squared is greater than or equal to nr. And once we plug these things in, like t plus epsilon minus L for n, and r is t plus epsilon, then we have t plus epsilon minus L plus 1. This is ugly. This is less than or equal to n times r, that's t plus epsilon, times t plus epsilon minus L. So now there must be ways that we can make this nicer, and there are. We can say t plus epsilon is something fixed, and let's call that something, actually t plus epsilon is r. So, oh yeah, I'll just make this so, oh, so this is going to be r minus L plus 1. Wait, I think I might have messed something up here. So n plus, this must be a positive integer. So n is, oh, this is, there's no epsilon here. This is t minus L plus 1. So then there's no good way, I think, to do this. We have what? Let's factor this. So now we get this. And my question for you is there anything you see here? Any way that we can finish this quickly? Well, actually, there's a much better way to even look at this, I think. Looking back now, I think like what we have is, this is t minus L plus 1 squared over t minus L needs to be greater than or equal to t plus epsilon. So if this is going to be true for some epsilon, like at least it has to be true for the smallest epsilon. So what we need is we need to have t minus L plus 1 squared is less than or equal to t times t minus L. For epsilon equals 0, it has to hold. If it's going to hold for any other epsilon, it's bigger. So this needs to be true. For our L, that is, what do we say? We said n is equal to the floor of r minus L, and we saw that these work. So we need to show that L needs to be less than 3. So now let's assume the contrary. L is greater than or equal to 3. And then what does this give us? Like, does this give us a quick contradiction? Like, that is the question now. And let's just make maybe, okay, let's say t minus L is equal to p, and then we have what? P plus 1 squared greater than or equal to p p times, what is this? P plus L. And now this p squared plus 2p plus 1 needs to be greater than or equal to p squared plus pl. Take this out, and we have 2p plus 1 needs to be greater than or equal to pl. And we need to use the fact that this number, I feel like now we'll use the fact that this number is, what's it called, that r is greater than 2. So here, what do we have? This is 2p plus 1 greater than or equal to this. This implies, I believe, like if L was equal to, so this is t minus L, t minus L is equal to n. My God, I'm just like using definitions back and forth. So this means that, okay, so now what is n? Let's just like take a moment to double check this. Well, this implies if n is greater than 1, this implies that L must be less than or equal to 2. So this gives us that upper bound. And now let's put all of these ideas back together and write up a solution. I invite you to do just that and see if I made any mistakes anywhere along the way for the next 10 to 20 minutes. Here's the solution. So we first set up the problem up like this. From r is greater than 2, we have this. So what we really need is there exists an epsilon which satisfies this if for n satisfies this thing right here. And now we need to show that every n that satisfies this has a unique epsilon, which gives us a unique x. Thus, we need to show that there are at most 3 n that satisfy this, and at least 2 that do. And now we move on to the next step, which is we show that these 2 n satisfy the relationships, and we showed like this. We do it in these 2 cases. We said what r is equal to. And now with that, we move on to our third claim, which is, and now we get to the final part, which is this. We prove that this never works. And we first like do this sort of estimate for x, which gives us an estimate for n needs to be greater than or equal to 2. And now with that, we finish up the problem. We get this contradiction if L is greater than or equal to 3, just by doing these estimates. And then this means this doesn't work. This doesn't work for all L, like the floor of R plus L doesn't work. The other side does not fit, which means that the only possible solutions are n equals the floor of R minus 1, and maybe sometimes the floor of R minus 2, but it won't be anything else. This shows that there are either 2 or 3 solutions for every single R, which solves our problem. And the main thing here was to think of the problem in a different way, like starting from x squared is x floor of R, to look at what, instead of looking at it as a thing for x, you looked at what does R need to satisfy. Sort of, I mean, back and forth actually, like, you know that this is going to be an integer. And then like, what does that give you as bounds for x? And then you have what is enough, and then you finish the problem. And as always, thanks for problem solving.